Hey there guys, Mr. Midas is here, and in this video I'm going to go over signed area and definite integrals. So let's take a look at these because it's going to be kind of a long video here, so let's get into it here. So the first few you should try on your own here. So I would say take a look at the problem, pause it, and then I'll go over some of these. And I'm going to try to go over some of these first few very quickly. So you might want to either slow me down, because I know some of you watch me at like 2 double speed and sound like a chipmunk, but you might want to slow me down for some of these. I'm going to go pretty quickly, or pause me when you need. So we're looking at the idea of signed area. Now, signed area is what these integrals are. So an integral from 0 to 3 is basically the signed area. So I'm going to draw this 2x, and kind of goes like this, right? It's like a check mark, all right? And it this is at 1/2. All right, and this is at 0, 1. So, and this ends here at 5. So we're looking at 3. We're going from 0 to 3, and we're looking at the area above the x-axis, okay? So the integral from the definite integral from 0 to 3 is really basically the area under the curve, area under the graph from the graph to the x-axis. So we would just find the area of this using, simple, just some triangles here, base times height. All right, base times height divided by 2. And we do all the math, we're going to get 13/2. Okay, so signed area is the idea that we're looking at the area under the curve. Now this is, of course, if we have linear lines, but if we don't have lines and we have a curve, then we can't really find the area under there. We can approximate it, but in order to get it exact, we're going to need to use some calculus. So the way we're going to do that is using an antiderivative, or a definite integral. So we're going to say the definite integral from 0 to 2 of my function 2x squared minus 3x plus 2 dx. Okay, this gives us the area under the curve, this shaded area that we're looking for. All right, so keep that in mind when we're talking about all of this stuff on the definite integral and the fundamental theorem of calculus. So let's take a look at this, and this is just going to kind of lead us up to this fundamental theorem of calculus. We have this function of the derivative. This is a derivative function, and take a moment to try to see if you can figure out each of these. So what is the area under the curve from 0 to 5? So we're looking from here to here. All right, well, that area is just 5 times 3, which is 15, right? Because we're just looking at the area under the curve. So let's write an equation for f prime of x on 0 to 5. Well, the equation of that, obviously here, it's just a horizontal line at x equals 3. So I'm just going to have f prime of x equals 3. So if I took the antiderivative of that, right, the antiderivative, I'm going to end up with f prime, oops, not f prime, f of x equals, using the power rule, 3x plus c, right? That's how we did the integrals. But we know we have an initial condition here that we know f of 1 is 4. So if we plugged in 1 and we solved for c, c is going to end up being 1. So we'd have a function f of x equals 3x plus 1. Okay, so that's good. We've got our function. Let's see what our what did we get if we did f of 5 minus f of 0, basically going from 0 to 5, now that we have our function, right? Now that we have our function, if I plugged in 5 in there, I get 16. If I plug in 0, I get 1, which is 15. Hey, look at that. If I took the antiderivative and then I took the x from where I'm looking for the area, I end up with the same thing as the area. What? That's right. That's pretty crazy, right? So signed area. So let's look at the integral of f prime from -2. So what we're doing is we're looking at the signed area from here to here, right? So that's going to give me -1/2 times 1 times 2. That's this area here. Plus 1/2 times 2 times 4. That's this area here, which gives me 3. So if I found the area for this function, I get 3. All right, so let's write an equation for that. Well, that one, f prime, that's a line, right? That's just 2x plus 2. It's just a linear equation, 2x plus 2. So let me do the same thing I did in the beginning. You should have tried this. Try this yourself too before I go do this. You can always pause me. And then I get that. And I plug in 1 in for x. And I end up with a c of -3. So I'm going to end up with f of x equals x squared plus 2x minus 3. And like calculus magic, if I plug 1 in, plug -2 in, and subtract, I'm going to end up with 3. What do you know? It should end up with the same as the signed area. So if I just took the antiderivative and plugged and found the difference after I plugged in each of these values from -2 to 1, then I should get the same value as I would just looking at the signed area. All right? So that's the basic idea of the fundamental theorem of calculus. Let's take a look at it in terms of context. So let's suppose I have a position equation, okay? And let me find the displacement. So the displacement of the object is x of 4 minus x of 1, right? Which is going to give me, when all is said and done, and I plug in things, I'm going to get 9/2. The velocity is the derivative of that, right? It's the derivative of my position, which is going to give me -t plus 4. Let me go and graph that. All right, so that looks like this. Okay. And it says find the integral using signed area. So 1 to 4, I'm looking at this area here. Okay, I'm going to use 1/2 base times height. 1/2 base times height, which is 9/2. Look at that. Turns out the area under the velocity curve, or the integral, is equal to the displacement. All right, really key important idea here. So notice that all those answers came out to the same. That gives us what we call the fundamental theorem of calculus. Basically, if we take the antiderivative, all right, if we take the antiderivative and we evaluate it from A to B, we're just going to, from A to B, we're going to plug in B and subtract it when we plug in A, and that's known as the fundamental theorem of calculus. So let's take a look at 3 examples here of the fundamental theorem of calculus. All right. So here I have 4. We're going from 0 to 4 to square root y plus 1. So the first thing I need to do is I need to change this to y to the 1/2 dy. Now with these, you're not going to put a plus c. The way we're going to write this to evaluate this is we're going to do the antiderivative. So 2y to the 3/2 divided by 3/2, right? Just the power rule, plus y. Now instead of the plus c, what you're going to do with the definite integral is you're going to draw a line, and you're going to say, I'm going to evaluate that from 0 to 4. So 0 on the bottom, 4 on top. Okay? And then you're going to plug in 4 into your equation for your variable. Okay, so that's going to be, let's see, I'm going to have 2/3 here. Sorry, I'm going to have 2/3, so that's 4/3. 4/3 times 4 to the 3/2 plus 4. And then I'm going to subtract, and I'm going to plug in 0. All right, so I'm plugging in 4, I'm plugging in 0. Then I'm going to plug in 0. All right, this is all 0, so then I'm going to just put that all together, and I'm going to get 44/3. Okay, let's try another one here. Okay, same method here. So we're going to notice here, though, I've got a 4t, right? So the derivative of 4t is 4, right? The derivative of 4t is 4. So I'm going to, in green here, I'm going to do a little reverse chain rule. So I need a 4 here and a 1/4 out here to do my little reverse chain rule. Okay, now I can go and do my antiderivative. So 1/4 times 4t plus 1 to the 5th divided by 5. No plus c. We're going to go from 0 to 1. So I'm going to plug in 1, and I'm going to get 1/20th times 1 to the 5th. Oh, sorry, 5 to the 5th. Oh, I forgot to add. Come on, my s's. So 6. Okay, 1/24 times 4 is going to be 4 times 1 plus 1 is 5 to the 6th. Minus 1/4. Remember, I'm going to plug in 1 and then I'm going to plug in 0. So 4 times 0 is 0, which is going to give me 1 to the 6th over 6. All right, I'm just going to go and leave it like that. All right. 5 to the 6th is a big enough number. I'm just going to leave my answer in terms of, in terms of that. All right, so my last one here, we're going to need to do some u substitution. So let me show you what happens when we do u substitution with definite integrals. So let me rewrite this. I'm going to rewrite this guy as 1 to 5 x times 2x minus 1 to the negative 1/2. All right, so on the side here, I'm going to do some u substitution. So u is going to be equal to 2x minus 1. So u plus 1. So then this is the other thing you have to do. You have to change your limits when we do u substitution. So we've got to change these. Change when u sub. All right, so here's an easy way to do it. You're going to plug in 5 in for x right here. So when x equals 5, u is going to be equal to 10 minus 1, which is 9. When x equals 1, u is going to be equal to 2 minus 1, which is 1. So that's what I'm going to change my, my limits to. So now I'm going to go and do my u substitution over here. I'm going to have u plus 1 equals 2x. 1/2 u plus 1/2 equals x. 1/2 du equals dx. Make my substitution. Now, what substitutes? Instead of 1, I'm going to have 1. Well, that stays the same. Instead of 5, I'm going to have 9. Instead of x, I'm going to have 1/2 u plus 1/2. Instead of 2x minus 1, I'm going to have u to the negative 1/2. And dx, instead of dx, I'm going to have 1/2 du. Okay, so now we've got to distribute this in here. All right, so I'm going to have 1 to 9 of 1/4 u to the 1/2 plus 1/4 u to the negative 1/2 du. And now I'm going to take the antiderivative. So I'm going to have 1/4 u to the 3/2 over 3/2 plus 1/4 u to the 1/2. And I'm not going to put plus c. I'm going to evaluate this from 1 to 9. Okay, let me do a little bit of math here. This is going to be 1/6. I'm just going to simplify it just a little bit for us before we plug in the values. And this is going to be 1/2. Okay, then I'm going to plug in 9. I'm going to get 1/6 times 9 to the 3/2 plus 1/2 times 9 to the 1/2. And then I'm going to plug in 1. 1/6 times 1 to the 3/2 plus 1/2 times 1 to the 1/2. All right, do some math here. Square root of 9 is 3. 3 cubed, 27, divided by 6. Going to be 9/2 plus 3/2 minus 2/3 when we do all that together. And final answer is 16/3. Okay, so that is a bit of a chore to do with u substitution, but I did want to give you an example of that with u substitution because you got to make. So the thing about u substitution you got to remember is you got to substitute and change your limits of integration. Those are called our limits of integration. So you want to change those. Otherwise, for all of these other ones, you're just going to straight plug them in to find that definite integral. All right. So there you go, guys. That's the fundamental theorem of calculus. We'll see you soon. Bye.